Okay, good evening, everybody. Okay, and welcome to another session of organic chemistry. In today's session, we are going to finish our discussion on Chapter 8. And then after that, we will start Chapter 9. Okay. Chapter 8 deals with the chemistry of alkenes. Okay, but before we start the discussion on Chapter 8, just a couple of announcements. Our own work assignment for this week is due on Sunday, October 27 at 11 p.m. That's our own work assignment for Chapter 8. And then also, I have posted all of the materials for the next exam, which is scheduled for Tuesday, November 19. I've got the previous exam that I gave in fall 2012 already posted, so you may want to start taking a look at it. And also all of the PowerPoint presentations for chapters 9, 10, and 11. These are the chapters that we are going to cover for the next exam. Okay. Okay, let us start the discussion on Chapter 8. When we left on Tuesday, we were discussing the reactions of alkenes. So what we want to do now, we are going to finish up on this discussion. We will finish up with the polymerization reactions, which is free radical chemistry. We are also going to discuss the synthesis of alkenes because we did not get a chance to do that last time. And then a few other reactions, formation of cyclopropanes, we'll discuss that. So we do not have too many topics to cover in Chapter 8 today. Okay. Okay, so when we left the reactions of alkenes, we were discussing the various ways in which we could perform, use different reagents to react with carbon-carbon double bond. And for the most part, we discussed the addition reactions of alkenes and oxidative cleavage of alkenes. So today, let us continue with the oxidative cleavage. You could have a carbon-carbon double bond right here. React, of course, you know this, you react with osmium tetroxide followed by sodium hydrogen sulfide, and you get the addition of two hydroxy groups. I will say this is a syn addition reagent. This reagent here, this combination of reagent here, we say this is a syn addition reagent. In other words, those two hydroxy groups that are added to this carbon-carbon double bond will be added on the same side of the molecule. See here. Of course, this type of reaction we refer to as hydroxylation. Anytime you add two hydroxy groups across the carbon-carbon double bond, you refer to that as hydroxylation. Okay? As you can see here, with all addition reactions, we are starting with an sp2 carbon atom here, sp2 carbon atom here, and at the end of the addition reaction, we end up with sp3 carbon and sp3 carbon. Okay. The same reaction here, we see the same here, osmium tetroxide adding to this to form the 1,2 diol. The same thing here, 1,2 diol. Now, once we form the 1,2 diol, now we could then take that and react with this molecule here we call periodic acid right here. That is periodic acid. this here. Once you react the iodic acid with the 1,2 diol, you will cleave this carbon-carbon bond. Now what you end up getting here, on this carbon, this carbon becomes a carbonyl of a ketone, and that is the carbon that is attached to an alkyl group, if you look at it here. And the carbon that is attached to the hydrogen atom eventually becomes the carbonyl of an aldehyde. So if you look at this sequence of reaction, therefore, osmium tetroxide followed by iodic acid, the net result, the net reaction is the cleavage of carbon-carbon double bond to give aldehyde or ketone. If you notice this is similar to the reaction of the ozonolysis reaction, in which we have ozone followed by zinc. Okay, so this sequence of reaction here, osmium tetroxide followed by sodium hydrogen sulfide, which will give the 1,2 diol, and then you follow that up with iodic acid to give the ketone, and in this case the aldehyde. This sequence of reaction is similar to the ozonolysis reaction. Okay, so let us give you a couple more examples of this. Supposing we have this. And I do this. Step 1, osmium tetroxide. Step 2, sodium hydrogen sulfide. Okay. What does this do? What will this do to this material here, to this starting material? This reagent, what will it do? It will add 2 OHs across the carbon-carbon double bond. Very good. And then you follow that always with the iodic acid. Okay, then you are going to get the cleavage of this carbon-carbon double bond. Okay, so that this carbon here becomes the carbonyl of what? What class of compound? Of an aldehyde. Okay, and this carbon becomes the carbonyl of a ketone. Okay, so we have this. Okay. On the other hand, supposing we just give you this. Okay, what do you expect to get here? What do you expect to get? Two carbonyl, right? Of aldehyde. Okay. Very good. I say this is similar to ozonolysis reaction. Because if you take for ozonolysis, if you take the same starting material, sorry. For ozonolysis, if you take this, of course, step 1, ozone, and step 2, zinc in dilute acid. Okay, of course, we know that from here, you will go directly to here. Or you will go from here, osmium tetroxide, followed by sodium halogen sulfide. Okay, so in this case, this is a two-step process, whereas in the ozonolysis reaction, this is a one-step process right here. Okay, so let us go to another addition reaction. Let me go back here. You got this? Mm-hmm. Okay. Okay. Another type of reaction we want to discuss is addition of carbenes to alkenes. Addition of carbenes to alkenes. Now, carbenes are molecules, intermediate molecules, in which you have a pair of non-bonding electrons on carbon, and that carbon is only attached to two other atoms, or two other atoms. Now, if you take a look at this molecule here, you only have 6 electrons in valence electrons surrounding carbon in this molecule. So therefore, it is highly unstable, just as unstable as your carbocation. So this type of molecule referred to as a carbene, and they are very reactive. As you can see here, this carbon here could add to a carbon-carbon double bond to form a cyclopropane. Okay, let's give you some examples. How do you form the carbene? Oh, you want to go back? Mm-hmm. Okay. The formation of this is not a very general reaction, so if you take this here, chloroform, and you take potassium hydroxide, this chloroform here is capable of generating an intermediate carbene. We put a bracket around this just to show that this is not a stable molecule. It is only an intermediate molecule. And then the carbene could then react with any alkene, for example. We could do this. chloroform and potassium hydroxide. What do you get? You get your cyclopropane this time 2 chlorine atoms are attached to this. You could also form a carbene by taking this molecule here, diiodo methane, and you take a mixture of zinc and copper, that would generate the methylene carbene, and this here could then react with, if you have an alkene, to give you cyclopropane. Okay, I think I do have some other examples of.
What are the brackets for?
Oh, the bracket simply means that it is not, it isn't a stable, it is an intermediate molecule. Bracket means intermediate. It is actually not as stable as the carbocation, intermediate molecule. Look at a few more examples of okay, this is how the carbene is formed, but you don't need to worry about that. Okay, as you can see here, cyclohexene with diiodo methane, zinc copper mixture right here from your cyclopropane. And then you could take a straight chain alkene here, this carbon-carbon double bond, the same reagent you see here to form a 3-member cyclic molecule right here. See, our focus is only on this, on the carbon-carbon double bond. Keep that in mind. The same thing happens here. Take this carbon-carbon double bond, chloroform, potassium hydroxide to form the cyclopropane. Okay, of course, with the 2 chlorine atoms attached to this carbon here. Okay, yeah, you guys see writing? Okay. The third type of reaction we will discuss today is what we refer to as catalytic hydrogenation. This we also refer to this as reduction reactions. In other words, we are going to reduce the alkene. Reduction simply means anytime you increase the number of hydrogen atoms of an organic molecule, you say you are reducing that molecule. Okay? Increasing hydrogen atoms in an organic molecule equals to we call reduction. On the other hand, if you increase the oxygen content, increase in oxygen content, of an organic molecule we refer to this as oxidation. Okay. Remember when we were doing the cleavage using ozonolysis, we were referring to them as oxidative cleavage because we were oxidizing those molecules. At the end, we were increasing the oxygen content of the particular carbon atoms in the molecule. Okay, anyway, so the reagent to use for this is hydrogen and some catalysts. In this case, we are using platinum oxide, and this acetic acid here is a solvent. Okay, the same here. You see what we've done? Carbon-carbon double bond. We add in 2 hydrogen atoms across the carbon-carbon double. And this is a syn addition reagent. Syn addition reagent. In other words, those 2 hydrogens will be added on the same side, from the same side of the carbon-carbon double bond. Same thing here. Take a look at this. What have we done using hydrogen? In this case, instead of using platinum, we could also use palladium. Palladium as a catalyst. Of course, here we're using ethanol as solvent. Okay, what have we done? Essentially, what we've done here, we've added hydrogen here. Let us notice that initially we do have hydrogen to start with in this molecule right here and right here. So those 2 hydrogens are still there. And then the new hydrogen we've added, let's use red pen. Okay. So the net process of this reaction is the addition of 2 hydrogen atoms across the carbon-carbon double bond. Okay, the same thing here. Carbon-carbon double bond. What have we done? 1 hydrogen goes here, another hydrogen goes here. Of course, we know that initially we do also have hydrogen here, so that hydrogen is still here. Okay, so that is what this reagent will do. Now we could actually use this reaction, the hydrogenation. We call this hydrogenation. You can see here. We could use hydrogenation to determine the order of stability of different alkenes. Order of stability of alkenes. Now this is important because when we get to the synthesis of alkenes, we are going to be using this order of stability to determine what products are we going to form as major products. Now if you take a look at this, what we try to do here, this experiment here is measuring the heat of reaction of an hydrogenation process. Okay? Instead of calling it heat of reaction, we could also refer to it as heat of hydrogenation. Now, what kind of information do we get out of this experiment? We have trans-2-butene and we have cis-2-butene. And then we hydrogenate each one of them. And both of them give the same product, butane. Now for the heat of hydrogenation of trans-2-butene, 116 kilojoules of energy is released. On the other hand, for the heat of hydrogenation of cis-2-butene, 120 kilojoules of energy is released. Now what does this tell us? Anytime you break a bond, the amount of energy that is released is the amount of energy that was embedded in that bond. In other words, what have we done here? We are breaking this pi bond to form a sigma bond, to form all this single bond in butane, and both of these are giving the same product. So the fact that if you look at this, the cis-2-butene gives us more energy. This negative simply means that it is giving off energy. This is an exothermic reaction. Now it is releasing energy. That is what the negative sign is telling us. So the cis-2-butene reaction releases more energy than the trans-2-butene reaction. So the message here is, this carbon-carbon double bond in cis-2-butene has more energy than the carbon-carbon double bond in trans-2-butene, which is to say that the cis-2-butene is less stable than the trans-2-butene. So these are the kind of experiments we could perform in this case to determine the order of stability of different alkenes. So we could perform a whole series of experiments to actually establish the stability order for different alkenes. So in this case, we know that trans alkenes are more stable than the cis alkene. Now, let us now go to it. So now this is the order of stability. Okay, before I discuss it, let me give you this here. If I have this, if I have this molecule here, this is ethylene. That's the common name for this, or ethene, if you want to use the IUPAC name. That's the common name. Now, this carbon-carbon double bond, this is the simplest alkene that we could find in nature and in the laboratory. Because each one of these carbon atoms is attached to hydrogen atom, we say this is a non-substituted alkene. Okay, that is very important going forward. Now, supposing I replace one of the hydrogen with an alkyl group, say for example, I take this off, one hydrogen off, I replace with, let us use a generic alkyl group, just say R, to represent the alkyl group. At this point, we will refer to this alkene as mono-substituted, because we have replaced one of the hydrogen of the non-substituted alkene with an alkyl group. So we now call this a mono-substituted alkene. Now, if I remove another hydrogen, I replace with another alkyl group, what kind of alkene would that be? That would be a di-substituted alkene. Okay? So that becomes a di-substituted alkene. Now, if I replace another hydrogen with an alkyl group, this now becomes a tri-substituted alkene. A tri-substituted alkene. And finally, if I remove this hydrogen here with another alkyl group, I'm sure you guys know what we are going to call that. But now, this becomes a tetra-substituted alkene. That becomes a tetra-substituted alkene. So therefore, supposing I have this, what kind of alkene would this be in terms of substitution? What kind of alkene would that be in terms of substitution? Any idea? Huh? What is it? Dice, exactly. That would be di-substituted alkene. Okay? So that becomes a di-substituted alkene. Okay? And of course, I come here, replace that with our ethyl group, becomes a tri-substituted alkene. Okay? So you begin to see the pattern here. So now, so what we have here is the order of stability of the different alkenes. This is very important because when we get to the synthesis of alkene, we are going to refer back to this order of stability when we ask you what will be the major product. Because the major product will be that is the more stable. Okay? Okay, as you can see here, tetra-substituted alkene is more stable than tri-substituted alkene. Is more stable right here. Then tri next. Then the di-substituted, less stable than the tri-substituted. The mono-substituted is less stable than the di-substituted. And as we showed you in the experiment that in the last slide, the trans alkenes are more stable than the cis alkene. Okay. Okay. So that's so far so good, right? Okay, so before we, I think the last set of reactions of alkenes we want to discuss will be what we call the free radical reactions of alkenes. Now, this is the type of reaction that is used to make your plastic. I'm sure you guys have seen this kind of plastic before. This is your polyethylene bag. And the starting material is that little bitty molecule that we showed you, the ethylene molecule. That is what gives you this. Okay? You may not think that is possible, but that's what gives you that polyethylene bag. So now let us briefly discuss the free radical reactions leading to the formation of plastic polymer. So I would say free radical reactions of alkenes to give plastic polymers. Okay, polymers are of course long chain of molecules, very big molecules, are made up of small units small units of molecules. I'll come back to this. Okay. Polymerization reaction. Okay. There are 3 steps. One we call the initiation step. Then we have what we call the propagation step. And finally, we have what we call the termination step. And this is common to all free radical type reactions. Reaction that involves formation of free radicals. In the case of polymerization to form polyethylene, we will have to start with some what we call an initiators. Let us imagine that we have, for step 1, let us imagine that we have 2 chlorine atoms joined together, which is chlorine molecule. And in the presence of sunlight or heat, in industry, they actually use very high temperature for this. You could cleave, you get what we call the homolytic cleavage. If you recall the 2 types of cleavage in organic chemistry, we have homolytic cleavage. Here, we are using the fish hook arrow to indicate the movement of only 1 electron, because of movement of 1 electron. Keep in mind the regular arrow, we use that to depict the movement of 2 electrons. So what are we doing here? We are going to cleave this chlorine-chlorine bond homolytically so that 1 electron goes to this chlorine, the other electron goes to this chlorine. So therefore, what we have from what we call free radicals. Now this free radical now come reacts with an ethylene molecule. In this case, one of the pi electrons here will move to bond to this chlorine, and of course once that single electron on chlorine also moves, so now you are going to form a chlorine carbon bond right here, and this other electron here will move to this carbon here. So we have this. We now form another free radical on this carbon. Okay? So this step here, this is the propagation step. We are now starting the propagation step right here. step 2. Okay? So this chlorine free radical reacts with an ethylene molecule. In the process, you are going to form a free radical on this carbon here. And once you start that free radical formation on that carbon, then that reacts with another molecule of ethylene. Reacts with another molecule of ethylene. Guess what is going to happen? This here, this bond, the pi electron will break homolytically, form a bond between that carbon and that carbon. This electron will also move, so now you are going to form a bond between this carbon and this carbon. So now you have this. Okay, we form another free radical. Can anybody tell me what will be the next thing that will happen? What will be the next thing that will happen? I know exactly. It will react with another molecule of ethylene. And so we call this process here a chain growth polymerization process. Chain growth polymerization. So this now reacts with another molecule of okay. Call this here. Come here. And this electron here comes here. So now you form a bond between this carbon and this carbon. Another free radical. So you can see here, we continue this process. We continue this process until finally we've almost exhausted all of the ethylene that is in the reactor, and then two free radicals will join together. That terminates the process. Okay? So when you do this industrially, of course they know the amount of ethylene to put in the reactor, amount of initiator to put in there. They know the temperature, they know the pressure. So if they want a desired polymeric material. So what you end up getting, therefore, step 3, your termination step. Okay, so you have, if you imagine now, let me use a generic molecule here. Imagine now you have two free radicals joining together to form okay. So finally, at the end of this process, you have a long chain. Essentially, what you have is an alkane molecule. So your polyethylene bag is nothing but an alkane molecule. Long chain of alkane molecule, that's what it is. In which here, these two are methylene group, these two CH2 groups, it becomes your repeat unit. So those are the two CA2 groups that came from your original ethylene. So they become your repeat unit. So you could simply indicate that you have so many numbers of those repeat units by indicating using this N here. And N could be any number from 100 to several thousands, depending on the type of plastic you want to make. So you could actually design your process to make a particular type of plastic, depending on the length of the chain that you want to make. Yes.
Where's the second variety
It's in the reactor. So when you're making all of this, you have making all of this. Okay, for example, if this here, right here, okay, that's a radical. Instead of reacting with another ethylene molecule, once most of the ethylene is gone, two of that will join together. You see it? No, that is just the initiator. You start with the, I mean, if the chlorine joins to it, that will also terminate the process. Any free radical, any two free radicals joining together will terminate the process. That is true. Even the chlorine free radical could join with that and terminate the process. So any two free radicals could terminate the process, and then you get the termination step. Okay, before we leave, let me now give you the synthesis of alkene, and hopefully I will let you go before the end of before time today. I know I do owe you several minutes already. Okay, so before we finish chapter 8, let us discuss very briefly synthesis of alkene. Okay, well, let me take you back to this. Remember when we started with the polymerization, you could start for the initiation step, you could actually use a peroxide. Okay, and a peroxide is any molecule in which you have oxygen bond. We refer to as a peroxide. For example, this is hydrogen peroxide. Right? And anytime we say peroxide, it simply means that we have two oxygen atoms bonded to each other. So these peroxides are very easy to break. So we could break this homolytically to start the polymerization process. So in this case, benzoyl peroxide is actually used as the initiator here. And once you form that initiator, you can see here, it reacts with ethylene, it continues the process until you get a very big molecule of polyethylene. And any two free radicals will join together to terminate the process. I'll give you one second to finish writing. Okay. Before we leave, let us finish up with synthesis of alkenes. There are two major syntheses for alkenes that we are going to discuss. One, the dehydration of alcohol. Dehydration simply means you are losing the element of water. Okay. Dehydration of alcohols. Actually, I will call this catalytic dehydration. Acid catalyzed dehydration. Let us. Acid catalyzed dehydration aqueous. Say, for example, we have this. Okay, this is a secondary aqueous. Cyclo, hexanol. Okay, this secondary aqueous, if we take sulfuric acid in water, that is almost similar to hydration. Remember when we added water to carbon-carbon double bond? Basically the same type of reagent. But we could change the condition, either the temperature, the amount of solvent, to actually do what we want to do. Okay, so we have sulfuric acid, or sometimes you could also use phosphoric acid, which is this here. How many of you are doing the organic lab now? Anybody? Anybody? Nobody? Okay. Okay, next semester you will do most of these reactions in the lab. Okay. Now, so you take acid, in this case sulfuric acid, in the presence of water. What you get is this. You get a lot of water. So we refer to this as dehydration, okay? Because we are removing water. Now, if you notice what we've done here, remember most of the reactions we've given you so far with regard to alkane, we gave you the addition reactions, then we gave you the oxidative cleavage. Now, this type of reaction, this would be an elimination reaction. Remember, we gave you 4 major types of organic reactions, and the elimination reaction was one of those. In this case, what are we doing? We are eliminating this here, hydroxide, and this hydrogen, so the element of water is being taken out of this molecule. And in so doing, this is the reverse of hydration. Your sp3 carbon here, this sp3 carbon here now becomes your sp2 carbon. So we go from sp3 carbon to sp2 carbon when we do the elimination. Okay? Now, supposing we have this, supposing we have that, and I add this, we want to do a acid catalyzed dehydration of this molecule here. Okay, let me number this carbon here. Let us say this is carbon 1, carbon 2, 3, 4, 5, and 6. I ask you, what will be the major product of this reaction? We know what this reagent will do now. At this point, we now know that this reagent will do dehydration. It could also do hydration. So now keep that in mind. So we are now increasing the complexity of this particular reagent. Depending on the situation, it could do hydration. It could also do dehydration. Okay, I ask you, keeping in mind the order of stability of alkenes that we gave you earlier, what will be the major product of this reaction? Of course, it will be an elimination reaction. The question I have for you is, With the double bond between the double bond that is going to form, will it be between carbons 1 and 2, or will it be between carbon 1 and 6? 1 and 2, exactly. And because of the stability order, because that will give you a more substituted alkane. So therefore, so that is the kind of thing that you need to keep in mind. So now we expect that the major product will be this here. So this will be the major product. If I ask you to give me only one product, this is what you give me. But if I ask you to give me all of the products, then you will give me the minor product. Minor. Okay. Okay, so for example, also, supposing I have this. So in this case, you could see here, this is a tri-substituted alkene. And this here is di-substituted. Okay, supposing if I have this. What will be the major product of this? This is carbon 1, 2, 3, 4, 5, and 6. Okay, where will the double bond be for the major product? Between 1 and 6. Very good. Now, what other products are possible here? Let us say this carbon is carbon 7, and this carbon is 8. If I say, give me all of the possible products, what other products are possible?
1 to 2.
Between 1 and 2, okay, very good. Okay, what other product? What? 1 and
1 to 7.
1 and 7, very good. Okay, so we're giving you one major synthesis of alkenes, and that is acid catalyzed dehydration. You ask me why do we call this acid catalyzed? Before we go, I will tell you why when we give you the mechanism. So now let me give you the second major reaction that we use to synthesize alkene. That would be number 2. Okay, we call this dehydrohalogenation. Dehydrohalogenation. Does anybody know what this would be? Dehydrohalogenation. No, dehydro. halogen. Exactly. We remove hydrogen and halogen. Yes, exactly. So in this case, if we have this, and the reagent we use for that, in this case, we could use hydroxide. That hydroxide could come from sodium hydroxide or from potassium hydroxide. Okay, what is going to happen here? It is the elimination of hydrogen bromide from this molecule. So this is another example of elimination reaction. So in essence, the next process here, we are removing hydrogen bromide from here. Actually, it should be, let's see here. Let me, if we have potassium in there, this becomes potassium bromide plus water. But the next process is we are removing the element of hydrogen bromide, which is this here, bromine and one of these hydrogen. So it is an elimination reaction, and then we form an alkane. Okay, the little time that we have, let me give you a couple more, okay, mechanism. Okay, I just promised that we are going to do mechanism before we leave. Okay. Okay, so anyway, those are the two major processes for making alkanes. One is acid catalyzed dehydration. Yes. No, okay, I'm going to get to that. You see why it's KBR. Okay, when we get to the mechanism. Okay, so two methods for making alkanes. One is acid catalyzed dehydration, in other words, elimination of water from an alcohol to form an alkane. Then the dehydrohalogenation, removing halogen and hydrogen from an alkyl halide. This would be what we call an alkyl halide. To form an alkane. Okay, we could also use, instead of using alkyl bromide, we could also use alkyl chloride. Okay, let us finish up this chapter by giving you reaction mechanism. Let's do the one with the dehydrohalogenation first. Supposing if we have this, what happens? This will be one of the more common mechanisms for this process. If we have this, okay, we have the hydroxide here, of course, in form of potassium hydroxide. The first thing that happens, if you look at the mechanism, of course, there is a solvent there somewhere. The bromine carbon bond could break. The mechanism that I'm giving you here actually depends on the nature of the starting material. In this particular instance, since we are starting with this type of material here, we are going to break this bromine carbon bond heterolytically okay. In other words, those two electrons will move to bromine, and then we'll have this. This time we form a tertiary carbocation. The bromine is here somewhere. And then what is going to happen? What is going to happen? This hydroxide here will come here to abstract. This hydroxide will come here in an acid-base reaction. And then you go this direction. Okay, in an acid-base reaction, to abstract this proton here, or to pluck this proton, and then in so doing, you are going to release these two electrons to form a carbon-carbon double bond. So to answer your question, that is how we form the water. So therefore, we form the carbon-carbon double bond, water is formed, and then this Br here, the bromide, will combine with the potassium to form potassium. So that is how that happens. Yes?
What happens to the methyl group?
Oh, the methyl, this here. This methyl group?
Yeah.
Is it, oh, I'm sorry. Thank you. Okay, that's how we form that product. Okay. So that is the mechanism for dehydrohalogenation, at least for this type of molecule, in which your starting material, the substrate, this carbon here, is the bromine is attached to a tertiary carbon. Okay. When we get to some other types of substrate, then we'll give you another mechanism. That will be in chapter 11. Okay. So in this particular instance, the first thing that is going to form is a carbocation. And then from this carbocation, you now have the hydroxide comes in here to pick up this proton here, releasing the two electrons to form the carbon-carbon double bond, and that's how you form this. Okay. Another mechanism I would like to show you actually for bromination. Of alkenes. Remember we told you, if we have this, that, and we have bromine, okay, bromine reacting with a carbon-carbon double bond. We told you that in this case, we have this is a syn addition reagent. I'm sorry, this is a trans addition reagent. In other words, if you look at this here, one bromine comes from the top, the other comes from the bottom, right here, and the metal is pushed up, going away, and the hydrogen push up, also coming at you. Here, the bromine pushes this down, and the hydrogen is here. Okay, you can see this is a trans addition product. Okay, it's a trans addition product. In other words, those two bromine are attached. They're coming from opposite side of the molecule. Now, what is the mechanism? This is what happens. This bromine here, when it is getting ready to react with this here, move as close to the carbon-carbon double bond as possible. And when that begins to happen, because of the size of the bromine atom, we form what we call a temporary dipole. It's almost as though the electron is moving away from this here, because electrons do not want to be close to each other. So moving away from here. So therefore, we could think of this. This having a partial positive charge, this bromine here, and this one having a partial negative charge. And therefore, this bromine will now react as though it is an electrophile, and of course the pi electron reacting as nucleophile. So you have this attacking this here, right here, and this breaking away. Then imagine that you then form this point. We have bromine here, and we begin to form the going down. This point we have this here. I put this in bracket because really, if it happens, it is very, very transient. In other words, very temporary. Almost as though you are forming a carbocation here, but not exactly. So therefore, all of this non-bonding electron on this chlorine here, what it does, simply now attacks this. We form this intermediate molecule. Okay, we form that intermediate molecule, and that intermediate we refer to as a bromonium ion. Okay, we call it a bromonium ion. Very reactive. And then what is going to happen, keep in mind that we have this bromide here, it's also formed. The bromide that is released right here, okay? So that bromide will now come in. What does it do? It has only two possibilities. It will come in to attack this molecule on this carbon, okay, from the back. In other words, it cannot come from the top because the top is almost blocked, okay? And if it does that, this will go open up, and that's how you're going to get your trans product. Or it could also come from here. If it does that, this also opens up. Okay? And either one of those will give you an enantiomer. Okay? So that is how you learn from two products. Or this other product. If you come from here, let us say this is A attack and this is B attack. Okay, so this is B, give you that. If it is A, we'll give you this one here. Okay, so you now have bromine here and this other bromine here. Okay, so we call this compound B and compound A. A and B are enantiomers. Okay, and this mixture here will be optically inactive. Okay, so I believe we've come to the end of chapter 8. I should also say that this same mechanism applies when you form the halohydrin. Remember, if you also have, did you finish writing this? Okay. Same mechanism applies to, huh? Oh, you see writing? Oh, okay. Huh? The mixture is optically inactive. So you form a racemic which will be optically okay. Okay, now I was going to say that the same mechanism applies for formation of halohydrin. In other words, whenever you have, say you have bromine water or chlorine water, okay, in this case, if you have this, the first thing that happens say you have this, okay, the first thing that happens is the formation of the bromohydrin, the bromonium ion. From the bromonium ion first, and once you form the bromonium ion, then the water comes in, attached from the back, either from this side or from this side, and each one of those attacks will give you a different product. Okay, and this could open up, or this could open up depending on the attack, and so therefore, and that is how you get your trans product. So that is also a trans addition reagent. It does say we We have the attack from here. Of course, there you have and then you have the bromine here. Okay? And keep in mind, at this point, we also have this bromine is also here. Okay? Was it time? It's been time. Oh. And I promised I was going to give it. This is it. This is it. Okay. Now what happens now? The bromide now, we simply just bear with me. I promise one of these days I will give you extra time. I will give you time off. Okay, so this bromide here will come here and remove this proton from here, and that is how you now form your bromoiodine, finally. Okay? And that is why that reagent is also a trans addition reagent. Okay, so folks, we have finished with chapter 8. When we come back on Tuesday, we are going to do start with chapter 9. So I want to thank you for your patience today. Oh, it's only 1 minute. Only 3 minutes. 3 minutes, okay. Okay, let me give you back to our exam.
Will the end of this chapter be in my next test?
Yeah. It's part of the next year, yeah.